All right, so we're going to talk about solids today. And if you kind of think of how we progressed through um, geometry in general, we started off with just one-dimensional shapes, things like point, a line, um, and then we developed into two-dimensional shapes where we had the polygons that we studied in chapter 8. And then the last unit was all about finding area um, or perimeter or circumference of those items. Well, our last unit, and it's kind of a sad day, this is the start of the last chapter of geometry. Um, we're going to finish chapter 12 before second trimester, and then third trimester, we're moving on to Algebra 2. So enjoy these last couple of weeks, but we are now expanding to 3 dimensions. And that's the idea that we want to look at here is what do I have in these specific shapes? Well, this first shape is a prism, and we're going to officially define these later on, so you don't have to take super thorough notes right now. But I'd like you to notice it's a pentagon in front, and then it's a pentagon in back. So anytime you have the same shape that's continued throughout, that officially is a prism. Um, but it's more than just a prism, right? We want to actually name it. And how do we name it? We name it by its base. And since its base is a pentagon, we call this a pentagonal prism. So you're always going to name a prism by its base. Now notice, base does not mean bottom here. Base is referring to the shape that is continued throughout. So I think of it as it's got 5 sides in front. And if I just shade, I don't know if shading that in does it justice. I've got 5 sides in front, and then I've got the same thing in back. So it's the same shape from front to back. That's a pentagonal prism. Well, what happens if I've got a base here? It's a pentagon, but it doesn't continue on to a pentagon. It meets at a point. Well, this is still a pentagonal shape, but then it goes to a point. And anytime it goes to a point, that's a pyramid. Okay. Now, I asked you to send me a chat of this one, and there's actually more than one answer for this specific shape. The one that I was looking for is, if you think of it, if the bottom is the base here, that's the base, one of the answers is a triangular pyramid because it's got the base and it comes to a point, right? The other name, because this is actually a special kind of solid, and we're not going to get into the platonic solids, but there's 5 very special shapes that are kind of created, and they're created because they use the same side throughout. But you could have also called this a tetrahedron. Okay, and I think 1 or 2 people officially called it a tetrahedron. Yeah, we have a couple people throwing out tetrahedron, which is awesome because that's an extension of this. For right now, we're happy with recognizing it as a triangular pyramid. It's a pyramid because it comes to a point. Now, this one is another type of platonic solid, and its fancy name is a cube. That's supposed to be a U. But you could also name it, let's say that this was the side. Right? And I don't know if it's a square or rectangle, so I'm going to call it a rectangle to be safe. And I would call this a rectangular prism. And why is it a prism? Because this shape, in this case, if I call this the base, that base is the same shape throughout the entire solid. Okay. All right. So that was just a quick review of some solids and how we name them. Quick little quote, thinking is the talking of the soul within itself. And hopefully you guys think deeply about the concepts we're learning. We're actually going to jump right into the the notes today. And what I'd ask you to do is some of this stuff you've already learned. If you've learned it before and you have it mastered, then you don't need to write it down. But if there's other stuff that you do, please write down. I'm going to give you the time you need to write it down. So we're looking at section 12.1 and 12.2. And our goal today is to start thinking about three-dimensional objects. And that's the approach we're going to take for the rest of this unit, is 3D objects. Okay. Well, we already threw this word out here, a polyhedron. I said name the polyhedrons, so you probably has made the assumption that a polyhedron is a solid. Well, there's something that has to be special about that polyhedron for it to be a true solid, is the solid has to be created using only polygons. Well, a polygon cannot have curved sides, or it can't have sides that just kind of stop and start differently. They have to be connected. Another way to think of it is a polyhedron is a solid that can be created with all of the shapes that we learned in chapter 8. Right? So if I look at this one, we named this a pentagonal pyramid. Well, what is it made up of? It's made up of one pentagon and then 5 triangular sides. Yes, Kamel just said only. So a polygon can only be made up with, or a polyhedron is only made up with polygons. It cannot be created with anything else. Otherwise, it's not officially a polyhedron. Really quick, I just want to, these words may come up every so often, so I want to make sure that we all kind of agree what they are. And when you look at a face, so what is the face of a polyhedron? It's considered one of the polygon sides, and we talked about it. This one has a base of a pentagon, so that could be the face, or I think I can do this. Here is one face, and it's a triangular face. It doesn't look great, but the edges. So what is an edge? Well, an edge is basically one of the side lengths. So an edge is the line segment where two faces meet. So you can see kind of right here, this edge is a line segment. And why is it? Because it connects the front triangle to the other triangle face. So it's a line segment that connects two faces together. And then the vertex is a point where 3 or more edges meet. So like right here, you can see I've got the edge from the top, the 2 edges from the bottom, they meet. So that's a vertex. And if I highlight all the vertex or all the vertices, can't forget the one up top. And we've used that word vertice quite a bit already this year. Now there is a relationship. We're not going to study it, but there's something called Euler's formula, and it relates for every polyhedron, every solid that's created with polygons, there's a relation between the number of faces, edges, and vertices. And it's just a quick formula. My guess is if you looked at enough of it, you guys could come up with that formula on your own. Okay, here's a challenge for you today. One of the things we're going to be focusing on is finding the surface area, right? How much space does the area of all the sides and the base take up? Well, to do that, we need to think of this as a net. So what is a net? A net is a two-dimensional representation of a solid. Okay? So what I'd like you to do is, can you draw a net of this pentagonal pyramid? I'll give you a second to just go ahead and try that. And by the way, I should have showed you, I'll show you how to draw this three-dimensionally as well. A little trick I learned on how to draw three-dimensional shapes. But go ahead and try to draw the net of this shape and see what you get. Okay. The first thing, actually, what I was going to show you, and I kind of forgot, was what's an easy or fast way to draw a shape like this? So how would I draw this three-dimensionally to start? Well, here's a hint. If you want to draw a pentagonal base, now notice it's not just a regular pentagon, it almost looks like it's flattened out. So what I would do is put my vertices first. So make your dots like this. And that's going to be the pentagonal base. And notice the back two sides are dotted. The dotted represents that we know they're there, but we can't officially see them. And then the front three sides are solid. And then pick a point right up top. Okay, that's your vertex up top. And then we know the back line is going to be dotted. And all the other lines connecting that are going to be solid. And that's how you can draw a three-dimensional pentagonal pyramid. So that's not the net, by the way. All that is the actual drawing itself. So how would I draw the net? Well, the net is basically the same way, except for instead of making that pentagon kind of laying back and more flat, we want to draw it normally. So I usually start with my dots. And I make my pentagon. Now, by the way that I'm drawing this is not the only way. But what if I took this vertex and I laid each triangle down on its side? So I would lay this one down over here. And then I would lay this triangle down. We should do our best to make sure that these triangles are all congruent. And if you're like me, your drawing skills are not awesome. But what I want to point out is that this vertex up top is really the same point. All of these red points would meet and come together and form right up top. So if that's true, then all of these sides over here have to be the same. So that means that each one of these triangles are exactly the same isosceles triangles. And you could even make the argument that this angle here is the same. Or you could make the argument for the other base angles. You could even say that these sides are the same if we knew this was a regular pentagon. But here's the net. Okay, now what is a net? It's a two-dimensional representation of a solid. And what we're going to do then is we're going to calculate the area of each one of these, right? Here's 1, 2, 3, 4, 5, 6. And instead of officially calling it area, this is the area of the outside shape. So we're going to call this surface area. And all it is the area. Surface area is area of all shapes. And actually, I'm going to call it all sides added together. So if you know what the net looks like, we know how to find the area of triangles. And in this case, a really fast way would be find the area of one triangle and times it by 5, because all these triangles are the same if the pentagon is a regular pentagon. The challenge is how do we find the area of the pentagon? And that's something that we actually did not cover. So we're not going to do a lot with the area of pentagons or hexagons. We're going to stick to rhombuses, rectangles, trapezoids, squares, and all those shapes that we've already learned last unit. Okay, so we're going to try something new here, and I'm curious how well this will go. I don't want you to write these down at all, but I got a little challenge for you. I'm going to send you a link of a website that you can use to create a net for yourself, and then your goal is, can you create a net of the following items? So let me show you first. This is just a little bit of a tricky website. It's going to look like this, and I'll send you this link in a second. But when you scroll down, you have solid and you have net. Now, you can do this yourself, but what I'd like to do is I'd like you to play around with this, and we want you to create your own. So what I want you to do is create a net. Yes, this one unfolded, but I'm going to reset, and I want to try to create my own. Oops, that should be down here. So if I hit create my own, then that's what you're going to have to do. So you're going to have to go create your own net, and then you can play with the zoom level if you want, but you're going to drag this in. And let's say that this is your base. And if I want to connect more than one shape, so I'm going to drag this over. Now what I can do is if I click on this shape, one of the sides will have a dot, and I can rotate it. And then it'll snap into place. So if I bring this one actually should snap in normally. But like, let's say I wanted to snap in here. All I have to do is rotate it, and then it snaps right in. Okay, now I could keep building off of that if I wanted. I'm not saying this at all is the right answer, but I'm going to put it together. If for some reason you put the wrong one in the wrong spot, you just hit reset and it'll start over. Or if you accidentally if you want to get rid of one, I think cutting it, you can click on it or erase. That's it. You just go hit erase, and then you can put it on there. And you can zoom in and out if you want. So I'd like you to try this using this site. And your goal is, can you create the following shapes? Unfortunately, I won't be able to see if you're doing this or not, which is fine. But I've got my potential answers down here. Now, the only thing I'll say is these answers are not all exactly, there's more than one answer to every single one of these. So if you do it one way and I do it another, that's completely fine. All right. If you look in the chat, I just sent you that link. Remember, the first thing you need to do is go to the drop-down menu and go to create my own net. And I'd just like you to try this, and we'll give you a couple minutes on it. See if you can create each one. I think you might even be able to create more than one you might be able to create them all on the same slide without erasing any of them. So when I show you my answers, you can check. Okay, so hopefully you had a chance to play around and create your own net based off of the images that we have here. There's a couple of these that are already set up, so I'll see if I can do this the way I want it to. What does a cube look like? Here's one potential answer. So if I take my cube, you can kind of spin it and see it. See if I can make this a little bigger. There we go. When I hit net, it actually forms out into the two-dimensional shape of that net. So here's one potential answer. I think I might have given another answer for mine. So let me see here. Yeah, I drew a different one. Just to show you that, you know what? The way you do a net or a cube does not always have to be the same as long as you have in this case, it would be a left and a right, and then the four congruent sides. Okay. The next one was the tetrahedron. So let's go to the tetrahedron, and here's the shape itself. You can see I can rotate it a little bit just to get a visual of what it looks like. It's the same on all sides. And if that turns into a net three-dimensionally, this is one potential option, which is kind of an interesting way to view this. It's a parallelogram. So we could take the base times the height, and that would give us the total surface area of that. Now, it would be a little bit, we'd have to be creative with finding the height, but you could totally do that. And I think that's just a really cool connection. But here's the way that I created the net for this one, is I took the base here, which was just the triangular solid, and then I just folded down all three sides. And this is another way for us to view a net. So what about the pentagonal? I'm not positive if this one has a pentagonal. It doesn't. This just has the, you could play around with this, maybe you already did, but here's the octahedron. If you've played the game Sims, this might look familiar. You could turn that. This one's kind of cool, a dodecahedron. I like the net of that one. A little funky. Icosahedron is made up of, I think it's 20 triangles. You could watch that turn into a shape and then take a look at it. So, yeah, these only have the platonic solids. So we're not going to deal with platonic solids, but notice what's special about each one of these. Each of these five solids end up having the exact same side. So it's a solid made up of the exact same piece all the way around. Right? This one was made up of, I think it was 20 triangles. Okay, so what does your pentagonal prism look like? Here's one potential net. It has two bases. Notice base does not mean bottom, right? I think this is one of the reasons why I wanted to show this piece right here is when I say base, right? The base is not the bottom, but it's the shape that's continued throughout. So I have a base up front, and then back here, I've got the base on the bottom. And then notice all of the sides are the same shape. They're all rectangles or maybe squares. I'm not really sure, but that's the idea here. Here, the base happens to be the same for all of these. So in this case, if I called the base the left side, that would be over here. This base on the right side here and the left side here, those would both be the bases. Okay, so let's put that away. That's just a visual piece of how you can deal with nets, because nets are going to be our way to approach a problem like this. So our job is to do surface area. And we're going to do this in pieces, just so I know you're in the right spot. Our job is to find the surface area of the following shape. Well, what is surface area? We defined it on the other page. It's the sum of the areas of the polyhedron faces, which is just a fancy way of saying add up all the sides, and that is how much total space the outside of our shape takes. So, find the surface area of the rectangular prism. Well, to do that, we need to draw a net first. So I'll give you a second to get caught up, and I'd like you to draw the net, and if you can, find the area of each piece, and then I'm going to have you do a zoom pull in a second. So I'll give you some time to get caught up on this. All right, now let's look at this. I want to draw this specifically to this shape. We don't have to officially pick a base in a rectangular prism, but in this case, I'm going to refer to the front side as the base. And I want to do that just so you guys have a frame of reference of how I'm going to draw this. So I'm going to start with this base right here. And I know that it is a 5 by 10 centimeter base. And then if I was to extend this side, the side on the right, out, and again, it does not have to be drawn perfectly, right? But I know that this length here is 5, right? Because it's the same over on this side, so that's 5. And then I know that this length is not 10, but it's the depth going back. So that's 8. Okay. And then what if I flip the top part up? If I go up off of this one, that's the top part here. Well, that's 10 by 8, so I know that that's 10, and if this side was to match up with this side, it would have to be 8. And you could put congruent markings if you'd like as well. Well, if I flip the other side on the left here, the side we can't see, if I flip that out, it's going to be the same. That's 8 by 5. And if I flip the bottom down, that's going to be a 10 by 8 as well. And I have every side but the back. And if I draw the back the same color as I drew the base here, that could be up top or it could be on the bottom. It doesn't really matter. Maybe I'll just put it up here. But that's the base that is continued throughout the solid from front to back. Okay, so now I know that this green shape has to be the same as this one here. So it's also 5 by 10. All right, so there's my base with all the 4 sides around it, plus the other base that we can't see. Again, you could draw this in many different ways as long as you have the shapes set. What I'd like you to do now is calculate the area. Find the area of each piece, add them all together, and then tell me which zoom pull answer is the correct one. All right, so we got 14 people who responded to the Zoom poll. We're going to give you another minute to finish this one up. All right, so if you didn't do so, make sure you log in your vote. Which answer do you think it is? I'm going to close it in 15 seconds. All right, so overwhelming result of A. Let's take a look and see which one is accurate, which one is right. So what do we need to do for this problem? Let me stop sharing so you guys can see the problem again. We need to find the area of each rectangle, add them up, nothing super crazy. A 10 by 5. By the way, you don't have to show any work for this. If you can do 10 times 5 in your head, I would just put 50 here. Now notice the units are centimeters. So when we find area, it's centimeters squared. And then here we got an 8 by 10. Here we've got a 5 by 10, but if you notice, this base is congruent to this base, so these have to be equal. And same thing here, this is an 8 by 10, so it's the same as the one above. And then the only other two is a 5 by 8, which is 40, 40, and then add them all up, and you should get your total surface area. And notice the units, 340 centimeters squared. Now, we show this to you because you've done this in the past, right? You've deconstructed shapes. You've drawn nets, I believe, in 6th or 7th grade, and you found area last unit. So this really isn't too much of an extension. I want to show you this really quick. I'm not sure if you want to write this down. It depends on how much you connect with what we just did. So I'm going to leave this to you. If you want to write this down, you can, but officially, what is a prism? We talked about it, but we didn't define it yet. So a prism is a polyhedron, so it's a solid with two congruent parallel faces. We call those bases. So it has two bases. Remember, base does not mean bottom. Okay? Joined by parallelograms, which are lateral faces. So our parallelograms are the sides that make up this solid, and we're going to look at drawing them here in a second. But I'd like you to practice drawing right now. I'd like you to draw a a hexagonal prism. It's not easy, so give it a shot, and then I'll show you how I would do it just to help you maybe make sense of this three-dimensional. All right, let's take a look at this. We'll talk about why it's called a right prism, but let's talk about a hexagonal. So hexagonal is six-sided. So I got to draw a six-sided shape, and one way to do that is just to make 6 dots kind of around in a circle, right? Same way we drew hexagons before. So if I draw that, connect it, and I'll ease your mind a little bit here, especially on a computer. We're not going to test you on your drawing ability. It's hard to do with a tablet or a mouse. But what do we want to do then is I basically want to take this shape and repeat it somewhere off to the side, right? And I kind of do it up and off to the right. And I want to basically try to make the exact same shape over here. Now, I've done this enough that I know a couple of these are going to be hidden. So I'm going to draw some of them as dotted lines because I know that they won't be seen if they're covered up. So that's not great. But now I'm going to connect the sides that go together. And we can just draw those in. And actually, you can see this one probably should have been a solid line. And then anything else is going to be the dotted lines that connect back. And I will tell you, in person, I could draw a much better one than here. But the thing that I want to show you is what do we have? The hexagonal is the base, right? That's the front part. But notice that base is the same in front and as in back. And then what are the sides made up of? Each side here is a parallelogram, and specifically, this shape is a rectangle. Now, why is it called a right hexagonal prism? Well, there's two different ways to think of this. We have one that's a right prism, which things just go straight up and down. If I was to take this and flip it around and made the hexagon the base, that would be straight up and down from the bottom. Okay. Or there's oblique prisms, and I'll just show you that. We're not going to do a ton with oblique prisms, but it's good for you guys to kind of understand what they look like. They're not super easy to draw. So I'm just going to draw one quick here. So what if I had a prism that looked like this? See how it's kind of slanted? This is not great. But you can see that this is at a slant, which makes it oblique, is because it has non-perpendicular faces, so that if we were to measure all the angles between these, every angle would be 90 degrees perpendicular to the bases. And in this case, this is not a 90-degree angle here to here. It might be 60 degrees or 30. Okay. Now, I don't think you need to write this, and actually, I'm going to leave it here as if you feel like you like the formula side of this, then what you'd want to do is you want to go back to the notes later on today. Okay? Um, there's a formula that we could have used to solve this problem here. But notice, if my goal is to teach you the way that you're going to make sure you connect conceptually, what is surface area? It's the area of each face added together. So let's think of it as a net and find the area of each face. Well, what did we actually do? We had two bases, right? In this picture, I've got a base here and a base here. So if I do 2 times the area of the base plus the perimeter of the base, well, why the perimeter? The perimeter is like the width of all of these rectangles, right? Each piece here added up gives me the perimeter of this shape, but then the height is the distance between the bases. So you could use this formula if you want. It's 2 times the area of the base plus the perimeter times the height. But I don't want to spend time on that today because I don't think you need this. But it is something that does exist. Just remember, the area of the base is something you have to calculate. Capital B does not equal lowercase b. And we mean that by the area of the base is capital B. It's how much space does this whole shape take up. Whereas lowercase b last unit represented just a single length. So if you're going to use this formula, you have to be careful. And then when we say the perimeter, it's the perimeter of the base. It's the distance around this object. There's my perimeter. And then what is the height? The height is the distance between the bases. Distance or length between bases. You don't have to write that down because we're not going to use it a ton. We're just going to use the net. Visually, we already talked about a couple of these, so that's why we're not going to write it. But when we talk about prisms, here are the shapes we're going to look at. We've got a base, and a prism has two congruent bases, and it's the same shape throughout. So it's a triangle on top and a triangle on bottom. Well, a cylinder is a special kind of base. It's just a circle, and we know to find the area of a circle. And then it's the same top and bottom. And then we have pyramids, and we talked about that at the beginning. Pyramids were a base, but then all the side lengths convert to one point, and that's the vertex or the top. So notice the difference between a prism and a pyramid. And then if the prism has a circular base, we call that a cone. Okay? Now a cone is probably the most challenging one to draw the net for, and that's going to actually come up tomorrow. What I'd like to do is we're going to work on this together just to kind of get you in the right frame of mind. I want to find the surface area of a right cylinder. Okay? So I'll give you a second to copy this. I had to handwrite these polls because the pi button, I didn't have time to program that in. But we'll do a Zoom poll here. And I want to make sure that you guys understand this at the start. Because a lot of times the struggle is how do I draw a net? And if we were live in person, I would have somebody come up to the board and try to draw this as I'd walk around and check to see. But think of a net. What if I took this and I opened it up into a flat two-dimensional solid? Well, the bases we know are the same, right? Those are pretty consistent. So I'd have a circle up top, the radius of 4. And then I have a circle on bottom, also with a radius of 4. But what is the other side what does it look like? Well, if I opened that up, think of it as like a can of soup. If you're like me, when I was a kid, I used to peel the labels off of all the cans, flatten it out, and what would it create? It would create a rectangle. Now we know that the height of this is 15. And here's the challenge. I have to find the area of this rectangle. And I want to find it by knowing this length. So my question to you is, what is this length right here in red?
The circumference of the circle.
Perfect. Awesome. Thank you. That is the circumference, right? Picture this. If I took all the way around this shape, that's where the label of the can would go, right? And if I cut it and then flatten it out, this perimeter or circumference of the circle is the same length as this shape. So there's my hint. And we do know that circumference is 2 pi r, right? So you're going to have to use that little formula from last unit to solve this. But I want you to take a minute, and now I'm going to release a new Zoom poll. And have you guys answer this one whenever you're ready. And you'll notice the Zoom answers, these are the exact answers, so we're leaving pi as is. Overall answer, 47% of the people said C. So let's see if that one is correct. We're going to go ahead and find the area of the base first. That's this circle and this circle. Now they're the same. And we know that the area of a circle is pi r squared from last unit. So if I plug in 4 squared is 16 pi. And if we look at our answers, they're all in terms of pi. So we're going to leave that as 16 pi. Now that's the area of both the top and the bottom, because these have to be congruent bases. That's the definition of a cylinder. And then I've got to find the area of this rectangle, which is base, which the base is the circumference, right? So I'm going to use the fact the radius is 4. 4 times 2 is 8 pi. So there's my base. And then the height is 15. So I'm going to take the area of this piece, which, by the way, I'll share this with you on the next page. This is called the lateral area because it's the area of everything but the bases. And all it is the area of that rectangle. 15 times 8 is 120 pi. So now, if I want to add up the area of the two bases plus the area of the lateral area, 16 pi plus 16 pi plus 120 pi, that gives me 32 plus 120 is 150 pi centimeters squared. So answer C, that was the one that was the most common. Okay. All right, be careful if you answered B, that means you found the area of one circle, but not the bottom. And just remember, the cylinder has a top and a bottom. So be careful on that. All right. I don't want you to write this. It's the same thing. If you like a connection to the formulas, then you could use this, and it will be in the notes. If you don't like it, you can do exactly what we did before. So what do we have here, though? Okay, we know a cylinder is a solid with two parallel circle bases joined by the lateral face, which we just drew the net of on the previous example. So how would I do this? It's 2 times the area of the base. Well, wait a minute. It's a circle, right? The area of a circle, we know. So I can actually come up with a specific formula for this one. Area of a base is pi r squared plus the perimeter. Well, that's always the perimeter of the base, and that's what Lexi just shared with us. That's the circumference, right? And we know that that has a formula, 2 pi r times the height of the solid. So if we really want to, this formula can be written specifically for any cylinder. Here's the surface area for any cylinder. But as we saw, we don't really need to memorize that because we can think of it as a cylinder. So if you want that, it'll be in the notes after class. I'll post it here. We don't have time for this example. There's one example I want to get to. I just want to show you this really quick because if they ask me to find the lateral area, that's the area of everything but the bases. So just really quick, I want to show you a visualization of this one. So if I drew this, I've got my base. Notice it's a triangular prism because it's a triangle in front and in back. And I could draw maybe this top part here. And I can draw the sides that connect it. Actually, you know what? Started that wrong. If I draw this side here, this is one way to draw the net. But the part that I want to show you is the lateral area. When we say lateral area, it's the area of everything but the base. And we kind of hinted at that earlier today. So then the bases are the triangles that are continued throughout. So if I ever ask you to find the lateral area, it's just the area of those 3 rectangles that are around there. And you could put the lengths on there. Notice this one is missing a side, but it's a Pythagorean theorem. So you could have to find this length using Pythagorean theorem and then do the rest. So just keep in mind that some of those skills that we've had in the past are always available for us to use. Okay, the last one is you have homework like this tonight on Delta Math, and I just want to show it to you. It's not worth writing all this down because you're going to see it on Delta Math, but notice what they give us here. Our goal is to figure out below is a net of a right rectangular prism. We know the surface area is 256 meters squared, and some of the areas in the faces are filled in below. Find the areas of the missing sides. So we have to find this area here and here. But notice, if this was my base and I constructed it, this base here is the exact same thing as this base here. So if I took all of the areas and added them up, they would have to equal the surface area of 256. So I could do 90 plus 90 is 180, 20 plus 20 is 40, and then A plus A is 2A. And you could solve this very quickly. Let's see, what is that? 220? Subtract 220, divide by 2. So that tells me that each one of these areas has to be 18 meters square. And that's the first part. The second part then is using your knowledge and finding the missing side. Well, let's look at this. If this length is already 9, then what does this length have to be to give me an 18 piece? And the only possible answer is this distance has to be 2. So it's 2 up top, 2 on bottom. And then since these are congruent, this piece here has to match this piece here. Those sides are also 2. So I just wanted to show you that in case you got a little bit confused, but that's how I would approach it. Take the areas that you know, reduce them from the surface area, and then work backwards to find the missing piece. Okay, so here's what we got, just so you know what's coming up. Tonight's homework is on Delta Math, 12.1 and 12.2, surface area of right prisms and cylinders. The formulas, if you want to use them, are available in the notes. As soon as I get done with class, I'll post them. And then on Wednesday, this is due. So your goal Wednesday, it's a little bit of a longer assignment. This is not officially due until Wednesday, and you're going to work on it today, maybe tomorrow, Wednesday, and then submit it. I will be available for help in my office hours from 1 to 2 today. So if anybody has any questions, please, please, please stop in and see me, and we can work through anything else. Remember, we only have a couple weeks left before the trimester ends. All right, so have a great day. We'll see you all later. Adios.